We're now going to talk about continuity and consider this definition. Let A be a subset of the real numbers, and let F be a function from that set A into the reals, and let C be a member of A. We say that F, the function, is continuous at C if given any number epsilon greater than 0, there exists a delta greater than 0, such that if x is any point satisfying x minus c less than delta, then f of x minus f of c is less than epsilon. This definition is very similar to the definition for continuity. There's only two differences. Instead of having like f of x, so here we have f of x minus f of c is less than epsilon. Whereas before we had f of x minus L is less than epsilon. That's different. And also we had that x minus c was less than delta. But in the limit definition, we had also that x minus c was greater than 0. So what that means is this time our x minus c can be 0. In other words, the value of x that may be included would be c. So this has to work even for c itself, for when x is equal to c itself. Remember, for the limit definition, it was any number x that such that x minus c was less than delta, but it was greater than 0. So this is slightly different in that way. So let's take a look at this. It's continuous at the point C. And then this up here would be, say, f of c. And then if for any epsilon that you can find, fc plus epsilon, fc minus epsilon. So for any epsilon you can find a delta. And again, you can make it as small as possible so that it'll fall, or I should say map to f of c minus epsilon to f of c plus epsilon. That would map somewhere in there. Like I said, you can pick it as small as you want, just as long as you can always find one. Let me just say, let me pick a delta, maybe something like this. We go c minus delta, c plus delta. And so you're saying that, okay, you can map within this range, and then you could always find the delta here that will map into here. And I'm just trying to think, when they state the definition of limits, one thing that's different about continuity is that you don't have the f of c has to also be within that range, but for limits it doesn't. I can't remember the way they state the limit theorem. F at c given there exists if x Oh, yeah, okay. The one difference is notice, and this is really subtle. So over here, notice the definition so that there exists a delta such that if x is any point of A satisfying x minus c less than delta, then fx minus f of c is less than epsilon. Again, so we can map into here. And notice that the way it's written here, x minus c less than delta. Now, this doesn't have to be greater than 0. So this could be 0. So in other words, f of c has to be included in here. In other words, or like, for example, you have to be able to put c in here. Even c has to be able to work. So any values here will map into this range here. Oops, sorry. Oops, something happened. Sorry about that. I don't know what happened. So any questions about that? So yeah, it's very similar to the limit, except it has to, you have to be able to put c into the function, and it still has to fall within that range. And so what I mean by that, and let me just show like an illustration here. And you, again, you did this in Calc 1, maybe not with these definitions, but remember, like, let's say if you have a function like this, say you had this f of c up here. And so like, say you're, well, yeah, let me do just like, for example, let's say if you have a picture like this, you remember from calculus, the limit, and let me say, so the limit, let me call this L right here. The limit as x approaches c of f of x equal to L. Remember from calculus, if you have a picture like this, the limit existed, I remember, but it's not continuous at c. Again, it's because when you, by the definition of the continuity, you have to be able to map every point into this interval. You have to be able to find the delta, that every point, including c itself. Whereas for the limit, it's okay to have it that c is a different value. Remember, I think in Calc 1 and 2, you took the limit from the left and the limit from the right. The limit from the left was L, the limit from the right was L. As long as that was true, the limit was L, and from our definition, the limit is L, but it's not continuous. And so that was another way you did it in Calc 1. Remember, you said that if it had any kind of discontinuities, that it was not continuous. In other words, if there's any breaks. So again, let me just show some pictures. Of course, if you have something like this, remember you said that was, so let's say at the point C, this was limit as x approach C of the function does not exist, huh? Because remember in Calc 1, the limits from the left, limit from right were different, so the limit does not exist. And of course, it's also not continuous. On the other hand, with the picture we just showed, if you have a break, however the break might be, could be up or down, the limit does exist. And let's say this is L here, but not continuous. That. So if you have any breaks in the picture, it's not continuous. And that's really what we just did a minute ago was kind of the formal definition of that stuff you did like in Calc 1 quite a bit. Any questions on any of that? And so let's just mention a couple of things here, and these are maybe outside the definitions. So again, that you got this from Calc 1 for a function to be continuous, at C, the limit must exist and also you could say it like this, F at C has to be equal to that limit. So what I mean to say is the limit as x approaches C of our function is L, and F of C has to be equal to L, like that. So it's kind of what I'm saying. Like in this picture over here, the limit existed. Obviously, it's going to be L, but we don't have, in this picture here, we don't have F of C is not equal to L. That's what kind of tells you it's not continuous. So that's sort of a few different ways of kind of saying the same thing. Any questions on any of that? And so we have another criteria. Again, this you didn't have in Calc 1, I'm pretty sure. It's called the sequential criteria for continuity. Let me give this a number. And function from, again, a set A to the reals is continuous at the point C in A, if and only if every sequence N in A that converges to C the sequence this converges to F of C. And what this means is you put every member of the sequence into the function, and that becomes the sequence, is kind of what this notation here means. And now it's pretty hard to really use this to prove something is continuous, but you can use this to prove something is discontinuous. And that's what they call the discontinuous criteria or discontinuity criteria. Let A be a subset of R and let F be a function from A to the reals. Let C be in A. Then F is discontinuous. At C, if and only if and only if there exists sequence X N in A that converges to C but the sequence Fxn does not converge to F of C. Like this. So in other words, you can use this, if you can come up with a sequence that converges to C, when you put the member of the sequence in the function does not converge to F of C. That's a way to kind of disprove that something doesn't have a limit. And I don't have any examples real handy. I think maybe next time I'll come up with some examples where you can use this, and it actually works out pretty nicely. But let me just do a couple examples related to continuity. Take a look at this one here. this example, let K be a constant greater than 0. And let F be a function from the reals to the reals that satisfies the condition that Fx minus Fy is less than or equal to that constant times x minus y. This is sort of like what they call a contraction. Now, usually it's a contraction if like K is less than 1. Now, they don't specify this here, but in other words, for any two values you can put in this function, there is this K value such that if you take the X and Y that you put in times that K, this will be bigger than the difference in the function. And this will be true for all X and Y in the reals. Show that F is continuous at every point C in the reals. So let's take a look at this. And much like we've been doing a lot already, do scratch work. And so once again, kind of get an idea what we want to do. Remember, we're going to have to bound, like, let's say, some kind of an X minus C. And so let's just sort of, a lot of times you can just sort of play with this a while, just with something informal. Because usually with proofs, you can't just kind of sit down and write them. You have to sort of get a feel for what's going on. Books usually just show you the proof, you know, and as though you can kind of just jump right to it. But in reality, sometimes it's hard to do that. So again, we have something like this. And what we would like to do, we can maybe even sort of work with this a little bit because we want to bound. So we want this thing to be less than epsilon. Now we want it to be true for, like, say, for each value of C. So we want, so we can rate that, say, for a specific value C, can't we? So for a specific C, we'll have like Fx minus Fc less than or equal to X minus C. Again, this is what we want, and maybe I should put it strictly less than to make it really correct. And remember, when we're doing our continuity, just like for limits, we want to bound this to make this happen. So this is what we want this less than epsilon, and we want to bound this. So bound X minus C. And so you can see what we can do right here. We could just rewrite this. We can say that X minus C is less than epsilon over K should work, huh? And then this will be our delta. That'll be our delta. And so now let's go ahead and see if we can write this out. So again, proof. Again, we wanted to do the same proof again for continuity. It's very similar to for limits. Let epsilon be greater than 0. And at some point here, we're going to say that C is a real number. Maybe we could even put that in at the beginning or after here. It doesn't really matter. Let C be a real number. So we want to make this show that this is true for all real numbers. And then choose delta equal to what we have over here, epsilon over K. Then for like it said here, you can say for all X or just say for all X that satisfies this. Again, sometimes you're writing this in your maybe your own way to describe it. A lot of people might say for all X such that X minus C is less than delta, but write it the way it makes the most sense to you. Implies, or we have, how you want to say the next line, implies that, again, remember we want to show that for continuity, f of X minus f of C. And now from the definition of our function, we know that this is going to be less than or equal to that K X minus C. And then over here, we've said that this is less than delta. And so we can say K delta. And then we said delta was equal to epsilon over K. And so this is going to be equal to epsilon. And again, you can just leave it like that. Or you can put one last thing just to, just to shade what you did, because i.e. f of X minus C is less than epsilon, as long as we restrict X minus C to be less than delta. And then we've set delta equal to epsilon over K. It works out that this is true. Again, once again, we're going back to satisfying our definition that we had a minute ago. So again, if we take a look at our definition, what we did, we wanted to show our function was continuous, say at a given point C. And so we let epsilon be greater than 0, just like our definition here says, and we found the delta greater than 0, that was based on that epsilon. And then we showed that by bounding X minus C to make it less than delta, that forced f of X minus f of C to be less than epsilon. And therefore, we proved that our function was continuous at the point C. That we're picking an epsilon, we're picking, like, say, a particular epsilon over here, and we want to find the delta that this is true. Now, in our case, the one that we just did here, we specifically said, okay, we're going to pick, if you pick an epsilon, so you're letting epsilon be greater than 0. So whatever one you pick, we're going to say, in this case, we said delta was equal to epsilon over K. And so what we're sort of doing down here in this specific case, we're saying, okay, this is, or delta is going to be epsilon over K. Epsilon over K. And so as long as we restricted X minus C toward delta, which was epsilon over K. And what that means, of course, is that means you're adding and subtracting epsilon over K. So for whatever epsilon you pick, if we pick this delta, these values will map within FC minus epsilon to FC plus epsilon. In other words, all anything that you plug into here will map to something into there, if that makes sense. Any questions? And so in this case here, because we were given this criteria, we said, and like I said, sometimes it's called a contraction. If K is like less than 1, it's kind of contracting what you're originally putting in. Here they don't say that, but still, we're still able to prove it's continuous, though, as long as we pick our delta this way, we can prove that we can map into that f of x minus f of c less than epsilon. Any questions at all? Okay, good. So let's look at some other things here. Yes, let me go on to some other, and these are this is actually sort of a review of what you had in Calc 1, a lot of the theorems, and you use these all the time. So let me just go through these kind of quickly because you use these quite a bit. You may not even realize it, but and this is combinations. Combination of continuous functions. And again, let me go through these kind of quickly. Let me just give a theorem here. Let A be a subset of the reals, and F and G are functions. On A to the reals, if F and G are continuous, at C, then the sum of the two functions are continuous. The difference of the two are continuous. The product of the two are continuous. B times G, where B is a constant, are continuous. At C. Again, like I say, you use these a lot without without even realizing it. If you have two functions, the sum of two continuous functions are continuous, the difference are continuous, the product is continuous. If you multiply any continuous function times where B is a constant, are also continuous. And then, of course, the quotient as well is continuous as long as the function in the denominator is not 0. If G is not 0, then f divided by g is continuous. So again, I went through that kind of quickly because it's stuff that you've kind of done a lot before. And another theorem, I'll call this 5.2.4. If f is continuous, at C, then the absolute value is continuous. At C. And of course, the converse would not be true. You can kind of imagine we can kind of think of something where, let's say, maybe even one thing that we had already, you could say this function, let's say you went from, let's say this was 1 and this was, let's say, -1 down here. And let's say this was -1, So this is our function. So the other way you can see doesn't necessarily work, like, say, in this case here, the absolute value of the function, what would that look like? That would be something, maybe it would end up filling this in, Then this will go here. And I suppose these ones down here, it would just kind of go up like that, So if you did so you can see the other way doesn't necessarily work. You can see this one would be continuous, but this one wouldn't. But if this one is, then the absolute value would be. Any questions on those? And some certain functions, polynomials, remember, they're always nice. They're continuous. Polynomials are continuous everywhere. Remember, if you were in calculus or calc 3, remember we did, if some of you were in calc 3 with me, and we did a lot of domains. Remember, polynomials, their domains are all real numbers, and they're also continuous at all real numbers. And also some other things like sine and cosine, they're continuous everywhere. If you think of the sine and cosine, continuous at all reals. Numbers. Again, a lot of that you've had before. And let me talk about continuous functions on intervals. definition, function from A to R said to be bounded on A if there exists a constant m greater than 0, such that you take the absolute value of x, the function of x is less than or epsilon for all x in the set A. Very similar we had for sequences, that they're bounded. Now for sequences, we just kind of just said that they're bounded. If they're bounded below and bounded above, they usually do a shortcut for functions. They just make an absolute value that takes care of everything. So it said to be bounded on A. So a function may or may not be bounded everywhere, but it's let's say could be bound on specific intervals. Like for example, you can sort of think of stuff like, let's say if you have the function f of x equal 1 over x, is bounded on the set, let's say, I don't know, 1 to 10, huh? In fact, the bound, what would be, since I guess the largest number would be 1, huh? The bound m is equal to 1 because that's the biggest number. On the other hand, it is not bounded on the interval 0 to 1, huh? Because no matter, if you, one thing you could even prove it's not bounded by some of the proofs we did before, you could say, okay, if you claimed that there was a bound, you could always find a smaller number, how to put in the denominator to make this thing blow up. Because it's just going to get, as you get closer and closer to 0, this thing is just going to blow up. Uncontrollably. So, like something like this, huh? So it's not bounded 0 to 1 or anything that would start with 0. But it is bounded. It's pretty much it's actually bounded on any other. If you put any positive number here, it's going to be bounded. So if you were to say, for example, it is bounded on C to 1 for any C. And I would say we want to restrict it to be small, to be positive and less than 1. So it's going to be obviously bounded for any that's getting washed out now. So it's bounded on C for any C. In fact, it would be bounded it is bounded by 1/c, huh? Any questions on any of that? And so a theorem that we have is called again, the boundedness theorem. Let I be an interval from A to B and be closed and let F be a function from that interval to R. Oh, thank God, I'm sorry. Thanks. You always holler whenever I do that. Thank you. Yeah, so let I be an interval from A to B, and then close, obviously closed interval, and let F be continuous function from that interval. Then F is bounded on I. So if it's continuous, it's bounded. Once again, it's a closed interval. Once again, for the example we had a minute ago, this comes up a lot for stuff. When we're going to talk later about uniform continuity, this comes up a lot. Once again, this is continuous on, let's say, once again, let me use a different one. Let's say on 1 to 5 again. Let's say something like this. And so it is bounded on 1 to 5. Now, it could be an open interval and still be bounded, like we had a minute ago. But again, if it's an open interval, it's not guaranteed to be bounded. So for example, let's use that same example again. F1/x is continuous on 0 to 1, but it's not bounded. So notice that 0 to 1 is open, so the theorem does not apply. Because the theorem only applied to closed intervals. So therefore, that's why you can find something here where it's continuous, but it's not bounded.